For 6 decades, we pointed our best telescopes at the largest planet in the solar system and thought we understood it. A gas giant, a storm world, a beautiful, swirling, distant thing. Magnificent, but knowable. We had equations for it, models, textbooks, confident diagrams, and confident journals written by confident scientists who had spent their careers building the most detailed picture of Jupiter that human civilization had ever produced. And then we sent a spacecraft into its heart. And everything we knew turned out to be a story we had told ourselves in the dark. Think about what it means to be wrong about Jupiter. Not wrong about a footnote. Not wrong about a minor atmospheric detail. Wrong about the deep interior. Wrong about the magnetic field. Wrong about the jets. Wrong about the very structure of the planet that may have made Earth possible. Jupiter is not just a planet we study. It is the gravitational architect of the entire solar system. It is the shepherd that hurled comets away from the inner planets for billions of years, that may have cleared the path for life on Earth to exist at all. And now we are discovering that everything we built our models on, every confident equation in every confident textbook, was built on sand. So here is the paradox that will follow you through this entire story. The planet we know best, the one we have observed longer than almost any other, the one ancient astronomers tracked with the naked eye thousands of years ago, turned out to be the one hiding the most radical secrets. The closer we looked, the less we knew, and the less we knew, the more extraordinary the picture became. So, are you ready to discover what NASA actually found inside Jupiter? And why it didn't just rewrite what we know about one planet, but potentially rewrote the rules of how planets form, how magnetic fields work, and what physics is even capable of doing at pressures and depths no instrument had ever reached before? I'm your host, and you're watching Dream Trips. In this documentary, we are going to travel to Jupiter, not as tourists, but as detectives. We'll start with what we thought we knew and why it seemed so reasonable. Then we'll follow the Juno spacecraft into one of the most hostile environments in the solar system as it peels back the layers of a world 5 times the distance from the sun as Earth. We'll sit with the scientists who expected to confirm their models, and instead had to rewrite them in real time. We'll confront the strange, almost impossible structures lurking at Jupiter's poles in its atmosphere and deep inside its core. Structures that have no clear explanation in the physics we teach today. And at the end, we'll ask the question that makes all of this not just scientifically important, but deeply personal. What does Jupiter's hidden nature tell us about why we are here at all? But before we can appreciate how much was overturned, we need to understand what we were so certain about. For most of modern astronomy's history, Jupiter was treated as a solved problem in broad strokes. Yes, there were details to fill in. Yes, there were storms to track and moons to explore. But the fundamental character of the planet? A massive ball of hydrogen and helium, layered like an onion, with a dense rocky core at its center, and smooth atmospheric bands flowing in orderly east-west ribbons around it. Felt secure. This picture had theoretical backing, computational models, and crucially, it had never been seriously contradicted, because no instrument had ever gone deep enough to contradict it. The problem with Jupiter is that you cannot simply look at it. When you point a telescope at the planet, you are seeing the tops of clouds. You are seeing the uppermost skin of an atmosphere that stretches downward for tens of thousands of kilometers, deepening into pressures and temperatures that no spacecraft made of conventional materials could survive for more than a few minutes. The planet is not transparent. It does not offer up its interior for inspection. It wraps itself in beauty and hides its truth. So scientists did what scientists always do when they cannot observe directly. They built models. They used the known laws of physics, gravity, thermodynamics, fluid dynamics, the behavior of hydrogen under extreme pressure. And they calculated what must be happening inside. The models predicted a layered structure. At the top, ordinary hydrogen and helium gas. Deeper, as the pressure increased, hydrogen would transition into a liquid. Deeper still, the pressure would become so extreme, millions of times the atmospheric pressure on Earth's surface, that hydrogen would enter a strange exotic state called metallic hydrogen, where it conducts electricity like a metal, giving rise to Jupiter's powerful magnetic field. And at the very center, most models placed a dense core of rock and ice, roughly 10 to 20 times the mass of the entire Earth, left over from the primordial clump of material that first seeded the planet's formation 4.5 billion years ago. This picture was elegant. It was consistent. It satisfied the equations. And almost every major planetary model we built, not just for Jupiter, but for Saturn, Uranus, Neptune, and even the thousands of exoplanets we have discovered around other stars, was built on the same fundamental assumption that giant planets have solid cores, dense, compact, a seed around which everything else accumulated. We were so confident in this picture that it became the starting point, not the conclusion, of almost every new study. You didn't prove the core existed, you assumed it and asked questions about its size. And then Juno arrived. The Juno spacecraft launched in August of 2011, and it took 5 years to reach Jupiter. 5 years of traveling through the void, looping around the inner solar system to pick up gravitational speed, before finally arriving at Jupiter's orbit in July of 2016. It was not the first spacecraft to visit Jupiter. Pioneer 10 and 11, Voyager 1 and 2, and the Galileo orbiter had all preceded it. But Juno was designed to do something none of those missions had ever attempted. It was designed to look inside. The spacecraft carried an instrument called a microwave radiometer, capable of peering deeper into Jupiter's atmosphere than any previous sensor. It carried a gravity science experiment so precise it could measure tiny variations in the planet's gravitational field as it orbited. Variations that encode information about what is happening thousands of kilometers beneath the cloud tops. And it carried a magnetometer capable of mapping Jupiter's magnetic field with unprecedented resolution. Juno was not just a flyby, it was a probe, a surgeon's instrument designed to open Jupiter up. What Juno found on its very first close pass, a screaming radiation-soaked plunge that took it from a distance of 50,000 kilometers above Jupiter's cloud tops down to within 4,000 kilometers of the planet's upper atmosphere, it was already remarkable. The radiation environment was so intense that Juno's electronics, shielded inside a titanium vault, still recorded more radiation dose per orbit than a human standing next to the Chernobyl reactor core would receive in a lifetime. Each pass was not just a scientific achievement, it was a survival act. But here is where the first surprise arrived. Scientists expected to find that Jupiter's atmospheric bands, those gorgeous alternating light and dark stripes you can see through almost any backyard telescope, were essentially surface features. Beautiful, yes, dynamic, certainly, but thin. The expectation was that these jet streams flowing east and west at hundreds of kilometers per hour probably extended maybe a few hundred kilometers down into the atmosphere before fading into a deeper layer of uniform, slowly rotating fluid. The atmosphere, in other words, was supposed to be a skin, a thin, active, colorful skin draped over a massive, featureless interior. Instead, Juno found that the jets do not stop. They keep going, down and down and down further. Jupiter's atmospheric jet streams, those banded rivers of wind that we have watched from Earth for centuries, extend roughly 3,000 kilometers beneath the cloud tops. To put that in terms you can feel, if you placed Earth's entire atmosphere, every molecule of air from the ground to the edge of space, and stacked it end to end, you would need to do that roughly 250 times to equal the depth at which Jupiter's jets finally fade into the deeper interior. These are not surface winds. They are vast continent-scale rivers of gas and liquid, plunging to depths that would crush any material we have ever engineered. And they have been flowing, continuously without stopping, for as long as Jupiter has existed. The researcher Tristan Guillot, a planetary scientist at the Côte d'Azur Observatory in France, who was part of the Juno science team, described the result as a revelation. The atmosphere was not a thin veneer. It was a massive dynamic layer carrying enough mass, enough angular momentum to measurably affect the planet's gravitational field. And Guillot and his colleagues realized something startling. If the jets extend that far down, then the atmosphere alone, not the core, not the interior, just the atmosphere, accounts for roughly 1% of Jupiter's total mass. That might sound small, but 1% of Jupiter's 3 times the mass of the entire Earth. Let that sit for a moment. The weather layer of Jupiter, the part we casually call its atmosphere, contains more mass than 3 Earths stacked on top of each other. But the atmospheric jets were only the first surprise. Because while Guillot and his team were recalibrating everything they thought they knew about Jupiter's outer layers, another group of scientists was getting their first good look at the core. And what they found there made the jet stream discovery look modest. Here is what the gravity data told them. As Juno orbited Jupiter, looping around the planet in an elongated ellipse, diving close, swinging far out, diving close again, the planet's gravity tugged on the spacecraft with tiny, measurable variations. Not large variations. Tiny ones. Variations so small that measuring them required tracking Juno's velocity to within a fraction of a millimeter per second, using the Doppler shift of radio signals transmitted between the spacecraft and antennas on Earth. The precision of this measurement is almost surreal. It is like standing in New York and detecting whether someone in Los Angeles just took a step forward or backward, based on how their footfall slightly changed the frequency of a radio wave. And the gravity map that emerged from these measurements told a story that did not match the models. The core of Jupiter is not what we expected. It is not a small, dense, compact ball of rock at the center of the planet. It is not the neat, solid seed that 4 decades of planetary science had assumed. Instead, the gravity data pointed to something strange. Something the scientists had no clean name for at first. The core appeared to be large, enormously large, and diffuse, spread out, diluted. The planetary scientist Scott Bolton, the principal investigator of the Juno mission at the Southwest Research Institute in San Antonio, was part of the team that first confronted this result. In interviews after the publication of the findings, Bolton described the initial reaction as deeply unsettling, not because the data was uncertain, but because it was clear. The signal was not ambiguous. The core of Jupiter was not compact. It was fuzzy. Fuzzy? That is the word the scientists actually used in the peer-reviewed literature. A fuzzy core. What does a fuzzy core mean? Here is the picture that emerged. 4.5 billion years ago, when Jupiter was forming, it may well have had a compact, solid, rocky core, just as the models predicted. But something happened. Something violent and enormous. The leading hypothesis, the one that the gravity data best supports, is that early in Jupiter's history, one or more massive protoplanets, perhaps objects the size of Earth, perhaps larger, slammed into the young Jupiter at enormous velocity. These were not the gentle accumulations of dust and pebbles that built the core in the first place. These were full-scale planetary impacts, titanic collisions carrying the energy of... There is really no human comparison that does the number justice, so let us try anyway. The energy released by a single one of these impacts would be roughly equivalent to every nuclear weapon ever built by every nation in human history, detonated simultaneously about 10 billion times over, per second, for thousands of years. The impact did not destroy Jupiter. Nothing short of a stellar collision could do that. But it did something nearly as dramatic. It shattered and dissolved the solid core, mixing the heavy rock and ice inward and outward, spreading the core material through a vast region at Jupiter's center. A region that spans perhaps 40 to 60% of the planet's radius. The solid core became a diffuse cloud of heavy elements, suspended in a sea of metallic hydrogen, dense enough to be detected, spread enough to be unmistakable, a ghost of the core that used to exist, haunting the center of the planet across a volume so large it dwarfs the entire Earth. And this is where the physics started to get genuinely uncomfortable for the scientific community. Because a fuzzy core is not just an interesting structural detail, a fuzzy core changes everything we thought we understood about how giant planets form. Not just Jupiter, but every gas giant in the solar system, and by extension, every gas giant we have ever detected around another star. The standard model of giant planet formation, called core accretion, depends critically on the idea that a solid core forms first, reaches a critical mass of about 10 Earth masses, and then begins to rapidly accrete gas from the surrounding disk. The solid core is the seed. It is the non-negotiable first step. But if Jupiter's core was destroyed by a giant impact, then the original solid core must have formed and been disrupted within the first 100 million years of the solar system's existence. A period when giant impactors were still flying around the inner and outer solar system in enormous numbers. Which raises a question that has not yet been answered. How many other giant planets in the galaxy have cores that were also disrupted? How many of the neat, clean planetary models we have built for thousands of exoplanets are based on an assumption that is simply false? The assumption that cores, once formed, stay intact. The short answer is we do not know. And the fact that we do not know is not a small gap in our knowledge. It is a chasm that runs through the center of modern planetary science. But wait. Before we go deeper into what the fuzzy core means for our models of the solar system, we need to talk about something that the Juno team was not even primarily looking for when the mission launched. Something they found almost by accident. Something that should not, by any conventional understanding of physics, exist in the form it does. The poles of Jupiter. Before Juno, we had never seen Jupiter's poles with any real clarity. All previous spacecraft had flown past Jupiter in roughly equatorial orbits, giving us glorious views of the famous bands and storms. The Great Red Spot, the white ovals, the turbulent regions, but leaving the poles perpetually tilted away from our cameras. Juno was designed differently. Its orbit was polar. It passed over both Jupiter's north and south poles on every close approach, giving scientists their first clear, detailed look at regions that had never been properly seen before. What Juno's camera revealed when it swept over the North Pole was not what anyone had expected. At Saturn, the North Pole hosts a famous hexagonal storm, a six-sided jet stream of almost geometrical perfection that has been churning for centuries. Scientists expected something similar at Jupiter, perhaps not a hexagon, but some organized structure. Some orderly pattern consistent with Jupiter's symmetric banded appearance at lower latitudes. What they found instead looked like chaos, but a particular kind of chaos. A chaos with hidden structure. The North Pole of Jupiter is covered by a central cyclone, surrounded by 8 other cyclones arranged in a near-perfect, regular octagonal pattern around it. 8 massive, rotating storm systems, each one roughly the size of the continental United States, locked in a geometrically precise ring around a central vortex that dwarfs them all. The South Pole was different but equally extraordinary, in a central cyclone surrounded by 5 storms in a pentagonal arrangement. These are not random storm systems that happen to be near the poles. They are organized, stable. They have persisted throughout the entire Juno mission, maintaining their geometric arrangement pass after pass after pass. Scientists watching them expected the storms to merge, the way storms on Earth tend to merge when they get close enough together. They expected the geometry to dissolve into chaos. Instead, the storms held their formation. Why? This question does not yet have a fully satisfying answer. The leading theories involve the interaction between the storm's rotation and the Coriolis effect at polar latitudes, creating a kind of equilibrium, each storm repelling its neighbors just enough to prevent merger, attracting them just enough to prevent dispersal. But the specific geometry, the specific number of storms, the specific stability of the arrangement, these remain active research questions. The physics exists to describe what we observe. It does not yet fully explain why what we observe is what we observe, and not something else. And then there is Jupiter's magnetic field. Jupiter has the strongest magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's at its cloud tops. Strong enough that if you could somehow see it with your eyes, it would appear larger in the sky than the full moon as seen from Earth. This field has been known since the Pioneer missions in the 1970s. What was not known, what no instrument had been precise enough to reveal, was the shape of the field up close, the fine structure, the texture. Earth's magnetic field, and the magnetic fields we had assumed for all giant planets, are roughly dipolar. North Pole, South Pole, smooth field lines running between them, like the textbook image of bar magnets with iron filings arranged in elegant arcs. This is what the simple models predicted for Jupiter. a large, strong, roughly dipolar field generated by the circulation of metallic hydrogen in the deep interior. Juno's magnetometer revealed something else entirely. Jupiter's magnetic field is wildly, almost incomprehensibly irregular. On one side of the planet, near the equator, there is a region of magnetic field pointing inward toward the planet's surface. A large localized patch of reversed polarity sitting in the middle of the broadly normal field. This region, which the scientists nicknamed the Great Blue Spot, in a deliberate echo of the Great Red Spot, has no real equivalent in our experience of planetary magnetic fields. It is a deep anomaly, a reminder that the field is not being generated by a simple symmetric process in a smooth, uniform interior. The Harvard planetary scientist Jeremy Bloxham, who led the magnetic field analysis for the Juno mission, described the field as unlike anything we had anticipated. The irregularity, Bloxham and his colleagues concluded, reflects something about the asymmetric distribution of metallic hydrogen in Jupiter's interior, possibly related to the very same impact event that disrupted the core, leaving the interior asymmetric in ways that create asymmetric magnetic generation. One side of the planet generating field differently from the other. A planet whose deep magnetic heart is not centered, not symmetric, not what the equations said it would be. Now you might be wondering, and this is the moment where we need to shift our perspective, because the implications of all this go far beyond Jupiter itself. You might be wondering what any of this has to do with physics being rewritten. We have described surprising discoveries, remarkable discoveries, but is surprise the same as rewriting physics? Here is the honest, important answer. Some of what Juno found falls into the category of physics being tested at extremes it had never been tested at before. When you discover that Jupiter's atmospheric jets extend 3,000 kilometers deep, you are not finding something that contradicts our equations of fluid dynamics. You are finding that those equations, applied to conditions we never had direct access to, produce results far more extreme than our intuitions suggested. The physics is not wrong. Our models, the simplified, computationally tractable models we used because we had no better data, were wrong about what the physics would actually do at those depths and pressures. But the core is different. The fuzzy, dilute, giant core is genuinely unsettling at a deeper level. The reason is this. The core accretion model, the model that says solid cores form first, then accrete gas, is not just a model for Jupiter. It is the foundational model for understanding how all rocky planets form, including Earth. The idea that solid material clumps together, forms a core, and then either stays a rocky planet or becomes a gas giant depending on how much gas is available. This is the story of how we think Earth itself was made. And if Jupiter's core was disrupted by a giant impact in the early solar system, that event almost certainly scattered enormous amounts of rocky and icy material into the inner solar system. Some of that material may have contributed to the late heavy bombardment, the period roughly 4 billion years ago when Earth and the Moon were pummeled by a ferocious rain of impactors. Some of those impactors may have delivered water to the early Earth, water that eventually filled the oceans. Oceans in which, billions of years later, the first living things appeared. Jupiter's disrupted core, the water on your planet, the atoms in your body. These things are not as disconnected as they seem. But here is where the story becomes truly strange, and where the phrase rewrote physics earns its weight, rather than just serving as a headline. The properties of matter at the pressures and temperatures inside Jupiter are not things we can reproduce in a laboratory. Not even close. The pressure at Jupiter's core boundary is estimated at roughly 40 to 70 million times the atmospheric pressure at Earth's surface. The temperature is estimated at 20 to 30,000 degrees Celsius, hotter than the surface of the sun. Under those conditions, hydrogen does not behave the way hydrogen behaves in any experiment we can run on Earth. Metallic hydrogen, the state that generates Jupiter's magnetic field, has only ever been produced in the lab settings for fractions of a second in tiny samples at pressures far lower than those inside Jupiter. This means that a significant portion of what we believe about Jupiter's interior is theoretical extrapolation. We have equations, quantum mechanical equations, high-pressure physics equations, that we believe describe what hydrogen does at those conditions. And Juno's data allows us to test those equations indirectly by seeing whether the predictions they make about Jupiter's structure match what the gravity data and magnetic field data actually show. And the result of that test is uncomfortable. In some respects, the predictions were close enough to be confirmed. In others, they were off by enough to suggest that our equations for matter behavior at extreme pressures, equations used not just for planetary science, but for nuclear weapons physics, for fusion energy research, for understanding the interiors of neutron stars, may need revision. The specific behavior of hydrogen-helium mixtures at those pressures, the specific way that metallic hydrogen transitions occur, the specific thermal and electrical properties of the deep interior, all of these are being interrogated by Juno's data in ways that will take years, perhaps decades, of follow-on theoretical work to fully resolve. This is what rewrote physics means precisely. Not that Newton was wrong, not that quantum mechanics is broken, but that the models we use to apply physics to extreme conditions, the equations of state that describe matter behavior at pressures and temperatures we cannot directly access, are being tested for the first time by real planetary data, and they are not passing all their tests. The physics community has to go back to the equations, with Juno's data as a new constraint, and work out what needs to change to produce a model that actually fits what the spacecraft found. This is how science works at its deepest, most exciting level. Not a dramatic collapse of everything we knew, but a precise, unsettling confrontation between our most careful theoretical predictions and hard reality. And reality, as always, does not care about the elegance of our equations. Imagine you are on the Juno spacecraft. Imagine this for a moment, because it puts what these instruments are doing in visceral context. You are moving at roughly 210,000 kilometers per hour as you dive toward the planet. The radiation is so intense that even the most shielded electronics on board are accumulating damage with every pass. Jupiter fills your entire field of view, not as the small disk you see from Earth, but as an immensity, a textured swirling wall of amber and cream and blood orange, stretching horizon to horizon and beyond. The cloud bands are not just colored stripes from here, they are living structures, each one thousands of kilometers wide, roiling with vertical motion, lit from below by lightning storms so powerful that a single bolt releases energy equivalent to thousands of Earth thunderstorms simultaneously. And beneath the clouds, invisible but detectable in the tiny, precise wobbling of your trajectory, in the subtle shifts in the magnetic field readings flowing from the sensors on your arms. Beneath all of that is the mystery. the diffuse core, the irregular magnetic heart, the deep jets. 40 years of models and the planet is still surprising you. That is what it felt like to be part of the Juno science team in the months after the first close approach data came in. Guillaume described it as a feeling of disorientation, like walking into a room you thought you knew perfectly well and finding the furniture completely rearranged. Bolton compared it to the early days of the Galileo mission to Jupiter in the 90s, when the Galileo probe descended into Jupiter's atmosphere and found far less water than anyone expected. An anomaly that still has not been fully explained, and that Juno's microwave data is only now beginning to shed new light on. The water question, in fact, is worth pausing on, because it is one of the places where Juno found something that directly implicates the history of the entire solar system, including Earth. Jupiter should, according to standard formation models, be enriched in water relative to the Sun. When Jupiter formed, it formed in the cold outer solar system, where ice was abundant, where the temperature was low enough that water, ammonia, and methane existed as solid grains, and those grains accumulated into the core that eventually seeded the planet. So Jupiter should have captured a great deal of water in the process, giving it a higher water abundance than the solar baseline. The Galileo probe, when it descended into Jupiter's atmosphere in 1995, found surprisingly little water. The planetary science community spent over 2 decades trying to explain this away, suggesting that the probe, which entered through a meteorological anomaly called a hotspot, an unusually dry downdraft region, had simply sampled an unrepresentative part of the atmosphere. Juno's microwave radiometer, capable of probing much deeper and across much wider regions than the Galileo probe's single-point measurement, has now confirmed that Jupiter's water abundance is globally variable in ways that are not expected from simple models. Some regions of the equatorial atmosphere show substantial water enrichment. Others show depletion. The average is higher than the Galileo probe found, which resolves part of the mystery. But the variation itself introduces a new one. Jupiter's water is not uniformly mixed. Something about the planet's deep atmospheric dynamics is creating pockets of water concentration and depletion on a global scale, in ways that our current models do not fully predict. And because Jupiter's water content is directly connected to the question of how much water was available in the outer solar system when the planets formed, and because some fraction of Earth's water is believed to have arrived via icy impactors from the outer solar system. This is not an abstract puzzle. It is a question that connects to one of the oldest and most profound mysteries in planetary science. Where did Earth's water come from? Jupiter's atmospheric chemistry holds clues that are only now beginning to be decoded. This brings us to the moment in our story where the science becomes something more than science, where the facts accumulate into a feeling that is difficult to name, but impossible to ignore. Think about what we have described in the course of this journey. A planet that formed 4.5 billion years ago from the same primordial cloud of gas and dust that made the sun, the earth, every human being who ever lived. A planet that was struck by a massive impactor in the solar system's violent youth, its solid core dissolved and spread through its interior like ink dropped in water. A planet whose atmospheric winds plunge 3,000 kilometers deep, carrying the momentum of weather that has not stopped since before life existed on Earth. A planet whose poles are ringed by perfectly arranged storm systems that should not, by intuition, be stable. and yet have held their geometry for every orbit Juno has completed. A planet whose magnetic field bears the asymmetric imprint of an ancient catastrophe no instrument had ever been precise enough to detect until now. And all of this discovered not by some futuristic technology we do not yet possess, but by a spacecraft the size of a basketball court, launched by a civilization that has only had spaceflight for about 70 years out of 4.5 billion years of Earth's existence. We are, cosmologically speaking, brand new. We have been asking serious questions about Jupiter for a cosmic eye blink, and in that eye blink we have already overturned decades of confident theory. What does that tell us about how much we do not know? Not as a cliché, not as the kind of humility that scientists perform at press conferences, as a genuine reckoning. If our models of the solar system's largest, most studied, most visible planet were this wrong about this many things, what else have we gotten wrong? What other confident pictures have we painted in the dark? The philosopher of science Karl Popper argued that science does not progress by proving things. It progresses by being wrong in increasingly specific, increasingly informative ways. Every time a well-designed experiment contradicts a well-built model, science does not fail. It succeeds in the most meaningful way it can. It discovers the shape of its own ignorance. And the shape of the ignorance revealed by Juno is not a small peripheral shape. It is a large central shape. It involves the cores of planets, the behavior of matter under conditions we cannot reproduce, the history of water in the inner solar system, the conditions that made Earth habitable. Jupiter was the gatekeeper, the giant that stood between the chaotic outer solar system and the fragile inner one, shepherding the orbits of comets and asteroids, protecting the terrestrial planets from the kind of continuous bombardment that would have made sustained life impossible. And for all that time, for all 4.5 billion years, you might have kept its secrets. Its fuzzy core, its irregular magnetic field, its impossible poles. Waiting. Not for us, because the universe does not wait for anyone, but available if we ever became curious enough and skilled enough and brave enough to go and look. We looked. We found more than we expected. And the story is not finished. Because here is the question that Juno cannot fully answer. The question that will require the next generation of missions, or perhaps the one after that, to even approach. What is actually happening at the boundary between Jupiter's rocky core material and the metallic hydrogen surrounding it? This boundary, this zone where the dissolved remnants of an ancient solid core meet the strange, electrically conducting sea of metallic hydrogen above it, is where Jupiter's magnetic field is generated, where the deep atmospheric jets finally fade, where the heat flowing from the planet's interior to its surface originates. It is the most important single region in Jupiter's interior, and it is the region about which we currently know the least. The gravity data gives us hints. The magnetic field data gives us structure. But the detailed physics of what is happening there, how the dissolved heavy elements interact with metallic hydrogen, how that interaction shapes the magnetic field, how it influences the heat flow that drives the jets above, remains almost entirely theoretical. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, launched in 2023 and is currently en route to the Jovian system, where it will arrive in the early 2030s. Its primary focus is Jupiter's moons, Ganymede, Callisto, and Europa, and the subsurface oceans that may harbor life. But it will also make observations of Jupiter itself adding new data to the picture Juno began to paint. And NASA is studying concepts for a future deep atmosphere probe, a successor to the Galileo probe, but surviving longer, going deeper, measuring chemistry and structure in ways no instrument has achieved. If such a mission is ever funded and flown, it would carry sensors directly into the regions that Juno has only probed from above. It would be the closest thing we have ever had to actually touching the inside of Jupiter. Until then, the boundary stays mysterious. The questions multiply faster than the answers. And that, in a way, is the most honest and most beautiful summary of where planetary science stands today. We sent a spacecraft to the largest planet in the solar system. We expected it to confirm our models. It did not confirm our models. It found a fuzzy core where a solid one should have been. It found jet streams that plunged to depths no one predicted. It found geometric storms at poles that had never been properly observed. It found a magnetic field shaped by some ancient asymmetry, bearing the fingerprint of a catastrophe 4.5 billion years old. And in finding all of that, it reminded us of something that science at its best always reminds us of. The universe is not obligated to be simple. It is not obligated to fit our equations or confirm our assumptions or satisfy our desire for clean textbook answers. It is simply what it is: vast, specific, indifferent, and endlessly more intricate than any civilization at any level of sophistication has ever fully grasped. Jupiter has been there since before the Earth had oceans. It was there when the first bacteria appeared in warm, shallow seas. It was there when the first fish hauled themselves onto land, when the dinosaurs rose and fell, when the first human beings looked up at the night sky and felt, for the first time, the ache of wondering what was out there. For all of that time, it kept its secrets. The fuzzy core, undisturbed. The polar cyclones, spinning in their perfect geometries, unseen. The magnetic anomaly, persisting across billions of years, patient as only something planetary can be patient. And now we know, a little more. Enough to know how much more there is to know. In the end, perhaps that is the deepest thing that Juno taught us. Not any specific fact about atmospheric depth or core structure or magnetic irregularity, as important as each of those is. The deepest thing it taught us is that the solar system we live in is still a place of genuine mystery. That the planet which ancient astronomers named for the king of the gods still has secrets worth discovering. That the act of building a spacecraft, filling it with instruments, sending it into a radiation bath on the far side of the sun, and listening carefully to what it whispers back across 700 million kilometers of empty space. That act is not just scientific procedure. It is a form of reverence. A way of paying attention to a universe that has been here far longer than us, and will be here far longer still. The question Juno leaves unanswered, the one that will follow planetary scientists for the rest of their careers, and their students' careers, and perhaps their students' careers, is deceptively simple. If Jupiter's core was disrupted by an impact 4.5 billion years ago, what exactly hit it? Where did that impactor come from? And if the same process happened to Saturn, to Uranus, to Neptune, what does the interior of each of those worlds look like? And how different are they from what our current models predict? We don't know. We genuinely, honestly, do not know. And in a universe this old and this large, not knowing is not a defeat. It is an invitation. Jupiter is waiting. And so, somewhere in the dark beyond our current instruments are the answers. The universe does not give up its secrets to the incurious. It gives them slowly and partially and with tremendous effort to those who keep asking.